Welcome back to the Generative AI Book Club. Per my own designs, we're trying to go through some of these later chapters in maybe a bit of a faster pace, get an overview of the topics that we find to be pertinent for our workplaces at the moment. Where we ended up last time is we started to look at fine tuning, and to the best of my knowledge, the overall idea is that you yourself might not be making an extremely large language model such as ChatGPT or Claude. However, you might want to fine tune it for your workplace to build a large language model or chatbot that could help you at where you're going. So what we're doing today is to look over some of the ideas in this realm of fine tuning. And as you can see up first, is the notion of low rank adapters, cleverly given the abbreviation LoRa. In particular, we're going to talk about dimensionality reduction. For a quick refresher on dimensionality reduction, I'll point us towards the ubiquitous Palmer Penguins dataset that many data scientists use. For the numerical variables themselves, there are 4 dimensions, and we think about how do we project this down onto 2 dimensions. On the left-hand side, bottom left, we see scatter plots 2 dimensions at a time. And on the right-hand side of the screen, we see what's called principal component analysis to try to express, in this case, 4 dimensions, but in only 2-dimensional visual space, while retaining as much variance or information as possible. The horizontal and vertical axes are called principal component 1 and principal component 2, respectively. And we could, in some sense, recover the original 4 vectors or variables, as you can see in the middle of the right-hand slide. From some linear algebra, you may recall a technique called singular value decomposition. It's a way to approximate an original matrix by the U, sigma, and V matrices that you see implied here. For our purposes, if you have a large vocabulary, say a data set on the order of 100,000 tokens, you would not necessarily want to deal with matrices that have 100,000 rows. What we're hoping for here, by reducing the effective rank or the number of linearly independent rows or columns, is to be able to save ourselves a lot of time and space on the computational side. What SVD does is we could reduce the situation down to, say, maybe 40 rows instead of 100,000 and retain a surprisingly a lot amount of information. The U and V are called as singular vectors, essentially eigenvectors, skipping some of the mathematical exposition, and the sigma diagonal matrix are the eigenvalues. These are ranked in a certain way to, once again, retain as much of the information or variance. And we try to keep or use only a relatively small amount of the eigenvectors instead of the whole matrix. Another thing to consider while we're here is when we're fine-tuning the weights of a neural network, we're essentially making slight adjustments to the weights. Say if we start off with a matrix of weights W0, we can make an update to W1, update to W2, update to W3. But if this is all additive, well, why don't we just keep in mind what the weights from the pre-trained large language models are there in the middle. Simply treat all the updates, all the additions or changes of the weights there on the right, and the final product, the weights combined, will be them added together. But what this allows us to do mentally is to take the original large language model, the one that was pre-trained by someone else, and just leave their weights alone. We freeze them. We do not have to change their weights, and then simply worry about the adjustments that we're making in our workplace. So what that looks like in a diagram, once again, the pre-trained weights on the left, the update weights on the right, we're treating those as separate entities and separate calculations before dealing with the final embedding, whether or not that's classification or regression. Now, on the right-hand side, what Laura is helping us do is, once again, with the dimensionality reduction. So rather than dealing with hundreds of thousands of rows, maybe break this down to maybe about 40 rows and save us a lot of time on the compute, the time and resources on the compute. This, of course, is our usual speed versus complexity trade-off. With a smaller rank.
Sorry, there is one question in that in the last slide. So that will mean that we have the pre-trained weights, then we do dimensionality reduction on the pre-trained weights, and then we do the update on the like the lower dimension weight.
So the update is on the lower dimension weights, yes.
Okay.
The pre-trained weights are not changed at all.
Okay.
So with a smaller rank of R, we of course are hoping for fewer parameters, faster training, and lower compute. But we have to acknowledge that unlike the larger rank of R, we're not going to be able to capture maybe all the information, especially if we're using neural networks to try to ascertain task-specific information in the first place. So for people who want further resources, there's a great CodeApp notebook, and there has been some nice documentation for giving advice to people in the AI community, practitioners, and the like.
Is there a difference between weightings and representation within the pre-trained data set?
The weights are literally the scalar multiples, whereas representations might be whole combinations of the activations.
Okay.
Just to mention this, I don't think I have this enough slides here. LoRa itself was in the resources that we have popular about 8 years ago, and as you can imagine, it's already being kind of updated. An update to that is called DORA, Weight Decomposed Low Rank Adaptation, and this is adapting from how we visualize, say, word embeddings or image representations as vectors. So each vector has a magnitude and a directional matrix. And we have the weights of being the magnitude times the projection matrices. And this has been an idea that's been thrown around for 8-bit. So I, for some reason, this particular slide did not show up, so I'll just kind of skip over it. I'll move into the next chapter, but as I'm transferring, feel free to ask questions. Continuing our discussion on fine tuning, we'll talk about reward models and reinforcement learning with human feedback. For the beginning of each of these slides, I just went ahead and once again listed out the resources in case anybody comes across these in this direction. So once again, thinking about what fine tuning is in general, the folks who were talking about this particular topic, RLHF, they wanted to remind us that there is a three-stage process here. One, we have the regular pre-training in general, and this is what I'm thinking about happens at the big companies such as Microsoft and Google. Two, what we might be doing at, say, a smaller company or university is the continued pre-training on a specific data set there. You can see it on D2 with the similar mentality that we discussed in the last chapter, separating the pre-training weights and the update weights. And then three, we would still need to bring this together, data sets D1 and D2, and continue training the large language model. Reinforcement learning. Sorry, these slides are not showing up. Just give me a minute here. I was trying to load each set of slides separately so I wouldn't have to do this production transfer between. Okay, so with reinforcement learning, I admit I only spent a few minutes talking about it a while back. Part of the mentality was that you would have a data set, and we talked last week about instruct fine tuning, how we could have a data set that was generated with humans in mind as to what are like positive and negative responses, good or bad responses. And you can see there in the middle of the diagram, human scorings involved. The whatever scoring mechanism you have, such as positive versus negative, would be the rewards in the reinforcement learning mentality. So there's a notion called preference classification, and the formula at the bottom is basically the softmax formula, but now applied to the rewards. And I bring this up in the terminology of it all. When we talk about reward models, we have a reward for a winning response, which is called at SW, a reward for the losing response called at SL. And we want to, of course, minimize the expected loss. Now, going through the terminology, we have SW minus SL, that's the difference between winning and losing. Sigma, that's an activation function such as the sigmoid. And taking a logarithm of this is a adjustment called cross entropy. Long story short, the reward model hopefully will work as intended, but if for some reason winning gets you much less reward than losing, that should be highly penalized against and removed from the system. So then reinforcement learning was human feedback, RLHF. Once again, apologies. I had pictures on many of these slides. And the thing is, if I go into the images folder, there's 100 images in there. It would take me a while to find it. Anywho, we're moving towards a notion called direct preference optimization. So I briefly showed you the formula on top, which I, once again, was coming from the softmax of reward models. Now we have a slight update to the formalization where pi reference is like a baseline policy, a baseline strategy for moving through a situation, and we're updating to a new policy pi. What we're hoping for is a setup where you could only improve, you could only get better guesses and minimize and further minimize your losses. So here's an example of what we mean by human feedback. As I was talking about a little bit last week, I actually have hope for making a lot of jobs for people and having them help feed and train the large language models. So for example, here in a generic picture, they would be supplied with a news article. And this is for the sake of censorship. You can see on the bottom right whether or not we want to eliminate perhaps this news article altogether from our training set. Otherwise, the human feedback would give this a rating on a Likert scale from 1 to 7. Now, when we look at the quality of the model outputs, literally what the chatbot is telling the user, at the time of this research, as you can see there in the bottom left, about 2022, the responses on a Likert scale from 1 to 7, the GPT responses were still rating at around 2.25. When we did a better job of learning how to prompt the GPT, the second line from the bottom, the model outputs got a score of about 3 out of 7. And with better scores if we increase the model size, going into the hundreds of billions of parameters, by the way. Now, when we do a little bit of reinforcement learning, in some circles that's called supervised fine-tuning, the second line from the top, we could see that the outputs, according to human judges, are getting better, with a score of about 4 out of 7. And the promise when we do a better job of having the human feedback, reinforcement learning with human feedback, now we're achieving the Likert scores that we see at the top in this system that they called Instruct GPT. And we're getting responses from our chatbots that are indeed viewed as favorable by the people that are using the programs. So some of the selling points of using some of these technologies, RLHF, the Instruct GPT with human feedback and whatnot, for the numbers on the left, you want them to be low. You want the toxicity, the harassment was reduced down to below 20% at the time. For the infamous hallucinations, Instruct GPT got that to be reduced down to be below 20%. However, at the time, supervised fine-tuning was doing a better job at about 8%. Getting the large language model chatbots to tell the truth, and in general, the numbers on the right, you want these to be larger. In the top right, to get the chatbots to tell the truth, Instruct GPT was getting values that are deemed around 40%, but compared to the predecessors, this was quite a big deal. And whether or not these chatbots were deployable for the sake of customer assistance, we could see that GPT supervised fine-tuning, we're already doing a good job at around 80%, but now this Instruct GPT was bringing this up to about 90%. So this all was becoming pretty promising. I'm going to once again transfer between chapters, but are there any questions about that?
So reinforcement learning with human feedback, I think we discussed at one point two ways of doing it, through supervised and versus unsupervised. I guess my curiosity is one necessarily better than the other? And do you see a scenario where supervised learning with human feedback is automated by the AI systems themselves?
Yes, I quite agree with that assessment. Diana, did you want to take a guess at that?
Just that, yeah, Brian, you said like automatize, like reinforcement learning from humans. I don't know if that removed the entire purpose of the task, or maybe I didn't understand that correctly. But like, yes, if you're gonna automatize like the human reinforcement learning, then it might not be that human, right?
Which will bring us, Brian, go ahead.
No, thanks for that, Diana. It's just something I think a lot about. Yeah, as we move on. Yeah.
And something that I was gonna ask Derek. So the in the last slide, so the instructor ChatGPT. So I guess you were talking about the ChatGPT 3, right? That was the model, like the base model, right?
So in that last slide, the base model was ChatGPT 2, and
Oh.
the technologies that we're talking about, yes, would lead into ChatGPT 3.
Oh, okay. Yeah,
Yes,
thank you.
you're right. This discussion will bring us right into the next chapter, direct preference optimization methods. I think out of my assumption of the preference of the people in this book club, and maybe myself too, we'll probably skip some of the mathematics. So like usual, overview. Usually abbreviated DPO, direct preference optimization methods. And it turns out, for as much as I wanted to talk about RLHF, reinforcement learning with human feedback, it turns out people move beyond that. So resources, and talk about a little bit more about policy iteration. So before, when we were thinking about RLHF, human reinforcement learning with human feedback, we have our preference data going into a reward model, and then making the policy for the language model, going through some of the reinforcement learning. What the developers realize is with direct preference optimization, we skip the middle steps altogether. So as you can see the quote on the bottom, if direct preference optimization removes the need for rewards models altogether. And if you're skipping a huge stage of your overall workflow, you can imagine this saved a lot of time and money in the training of large language models.
So I guess the creation of the policy in the previous method, that will be kind of like automating the human interaction for the reinforcement learning, right?
Yes, you're both nailing this right on the head. They automated the feedback process.
Yeah.
So again, without doing the entire proof, the idea was that we're getting policy iteration which leads to situations where the reward for the winning responses keep improving. And there are some elements of math theory coming from the world of reinforcement learning that show that convergent increasing sequences of policies do exist. So in other words, you can have assurance that your training of the large language model is going to get better and better, assuming everything else is set up correctly.
So I wonder if you can explain this graph. I know you showed this earlier in the DPO slide. I'm trying to understand the different values or the different constants here. What pi ref? Yeah, I guess some of the different constants here. I'm wondering if you could speak to.
So pi ref was once again be the old policy. Pi theta would be a candidate for a new policy, a new strategy, and you would only, being very careful to negative signs, you would only decrease the loss if pi theta is better than pi ref.
I see. The probability of X. Okay, it's okay. Well, thanks.
So let's look at some of these, and this was approximately 2023, a couple years ago. Look at some of these models that were being used, and as usual in data science, machine learning, etc., sometimes the best thing to do is apply different methods on the same data set so you can see which ones are doing better at the moment. Rewards on the vertical axis, so larger numbers are better, and we see various attempts to go beyond reinforcement learning with human feedback, RLHF. And you can see in the yellow dots, the direct preference optimization are seemingly doing the best in this data set, Internet Movie Database Sentiment, talking about whether or not movie reviews are positive or negative. So in particular, this experiment is run over what developers are calling quality data, in that you have no need for a reward model, which greatly decreases the need for human feedback for getting human volunteers. Because in this sense, you already have the data from a database. Another perk that the authors said of their direct policy optimization is that it's dynamic. Suppose that you work at a company that has new data every month or every quarter, you want a system that could improve upon it. And if you've ever taken Bayesian analysis, this is kind of an idea from Bayesian analysis. We briefly saw, at least in the human feedback realm, that you could be precise with your fine tuning. If there's an area of context that you want to censor out, say, for example, maybe in the medical field, you want to censor out anything that you know would be harmful, you could put that in your data set and you could move your language model towards that, or away from the harmful, I should say. The horizontal axis is Kullback-Leibler divergence, talking about the differences between distributions. And part of the reason why KL divergence is used in these training workflows is because you actually do not want your language models to move too quickly. You don't want them to, loosely speaking, change their opinions too much and still stick to some of their prior knowledge as well. I thought that this slide from one of our resources was pretty neat in particular. So again, various proposed systems for going beyond RLHF, reinforcement learning with human feedback. You could see some of them were called things like IPO, KTO, DPO, direct preference optimization, and this particular paper was written about something called Zephyr. On a scale from 0 to 10 on reasoning level in these 6 categories, it looks like all the models are doing very well in humanities, fairly well in writing and STEM reasoning. For those of you who do things like world building or Dungeons and Dragons, they're in the top right. Role play seems to be doing pretty well. But at the time of this particular paper, notions in extraction, such as maybe summarizing a research article, coding there at the bottom, were a bit lower in scale. Math was the lowest, but I want to remind my audience we're talking about graduate level math, talk about proofs and theory. Obviously, machine learning solved high school math and calculus a long time ago. So yes, I did not go much into the math of the direct preference optimization, but the resources, or at least the blog post, assured us that these were doing better than the reinforcement learning with human feedback. Once again, I'll take a moment to transfer between chapters and welcome questions from you all.
I just wanted to comment that I guess that the first line, having good quality data, like that will make like a huge difference between needing a rewarding step and not needing it, right?
Indeed,
it's
and there's a divide between what's supervised learning and reinforcement learning in the first place. Reinforcement learning, at least especially for video games, was situations where you did not know all the information in advance, and the agent has to figure it out.
okay.
Where in supervised learning, you have the whole data set in advance.
Yeah.
Good point.
Yes. Yeah, and I guess it will depend on the application of the model, like the subject and the data and the application, if we actually need a reward model or not.
Yeah, so also the way we're going through this generative AI handbook is we actually haven't talked much about the generative stuff, the making of the new data. So part of the thinking is to bypass the human feedback, is to have the AI generate the new data. And this is true also in computer vision and elsewhere in language models as well.
Yeah.
All right. As usual, thanks for your patience. We have a couple more chapters to mention today. Chapter 23 goes into context scaling. A week or two ago, Brian walked us through the notion of scaling laws, how developers are thinking about the growing of their task, whether it's growing the data set size, whether it's growing the model size, and of course, worried about the growth of your time and resources on the compute. What we mean by context is if you have a word in a sentence, as David was talking about back in Transformers, you might have a window size to the left or to the right, maybe looking 3 words to the left, 3 words to the right. And what we mean by context is similarly, like how far to the left and how far to the right can you go in an input. So the resources we're looking at right now is thinking about adapting to long context inputs And we probably should mention a update to positional encoding called rope. So the problem is when you have a bunch of different, say, lines of text, they have most likely a different number of tokens. Some inputs are very long, some inputs are very short. Now, what happens though is at the moment, the data loaders were assuming that each input had the maximum number of tokens. So there was a lot of blank space that had to be filled in with padding. This was quite an issue for memory usage, and something we might have discussed back in talking about transformers, the encoders and decoders, was that the space that you needed to store all the weights was on the order of n squared, quadratic scaling. So that is to say, if you doubled your input data set, you would quadruple the amount of space you would need to carry for the parameters for the calculations. And as you know from computer science, anything that's big O n squared or above is something to worry about or something to try to avoid. You don't want your compute time to grow by such a power or exponentially. So there have been some fixes that in the article, it was one of the think tanks. They just blatantly said, hey, over the past year, we have done so many ways to fix the problem. One of them is grouped query attention. When you think about the query, key, and value matrices from encoder, decoder, transformers, you might still have multiple query matrices, but instead of updating the other two, keys and values, you might use the same matrices over and over again. So that way you're not quite dealing with big O n squared there. Gradient checkpoint, when you're dealing with deep learning, say if you have 4 hidden layers, 8 hidden layers, 16 hidden layers, or so forth, you might make it a little easier on your system to only save the result after every few layers rather than after every single layer of your deep learning network. So they were recommending after every square root of n layers. Earlier in this hour, in a previous chapter, we briefly discussed LoRa, low rank allocation, in particular for the update weights. A week or two ago, Brian was talking about mixture of experts, and this idea gets carried forward in distributed training. We want to take advantage of parallel processes if and where possible. Sample packing, that is to say, if you have, I think I have the picture, never mind. If you have a lot of space because of the padding of the tokens, you might be able to put multiple sentences within each of the input data loaders, and that will save space as well, rather than just wasted space on padding. And then, to the best of my knowledge, one of the big deals in recent years and in the past 3 years is called flash attention. So rather than things, I don't have the mathematics here, but the punchline is rather than things growing big O n squared, now you could have multiple encoder transformers, and computational growth will only go up big O n. So it's much more, it's easier to handle for the think tanks to make their large language models and keep going up by orders of magnitudes, as we saw earlier, in the hundreds of billions of parameters now. We talked previously about position embedding. Developers have moved on to at least to rotary position embedding. It still uses sines and cosines for their linear independence, but it arranges them more like this in what you may recall is a rotation matrix in linear algebra. And the motivation is that unlike positional encoding, we want to have in particular, we want our positional encoding vectors to maintain their magnitude, to keep the same size. And this ended up being a more generalizable system in case you had scenarios such as reinforcement learning, where the test data in size was much greater than the training data. So those were a couple of the key points. And moreover, with positional encoding, you want systems that maintain the relationships. Say if two words are close to each other, their calculation of the positional encoding should show that they're close to each other, and vice versa for far apart objects. So some of the experiments, one of the resources was talking about which data sets they were able to utilize. So in terms of the number of tokens, they went from 1 million, 10 million, all the way up to 50 million. And for the context lengths, that is, remember, you could take a word and view a certain number of words to the left, a certain number of words to the right. And we want these context lengths to be very long, especially say if you want to summarize a whole essay, a whole research paper. So their context lengths were being pushed up from the thousands to the millions of tokens. So this was getting some promising results. With the Llama language models, we have these results in a metric called complexity, where lower is better, as you can see on the vertical axis. With the context windows, that is to say, how many tokens would be a part of trying to ascertain meaning. And you can see in the top right, several different prototypes were used in the Llama models. Some of them, as implied by the divergent virtually vertical lines, some models just started to completely fail at some point when we kept asking it to read more and more deeply in terms of number of tokens through the articles. But there was promise, with especially the green line in particular, that we could achieve the lower complexity scores and run these programs on larger text files. So again, the notion of context scaling is to go from basically from reading, having AI read a sentence to having AI read a paragraph, to now trying to get AI to read a whole article and maybe in the future read an entire book. One more time, transfer between chapters, and welcome questions from people in the book club.
The method that you mentioned when they get down to O big O n, so you said it was encoding, so that would mean applying multiple encoders like encoding data that it's already encoded?
I have not looked into flash attention myself, but I think part of it was if you have a lot of query key and value matrices,
Mhm.
it's an issue of whether or not they even keep the weights around, whether they keep that in memory or they delete old versions of the matrices. I think that
Okay.
was the idea.
Okay.
But yes, flash attention, which might come up elsewhere in the generative AI handbook, apparently was a really big invention along the way. It's probably what made things like ChatGPT 3 and 4 possible. All right, so when I was skimming through these materials, this whole section is about fine tuning. I just kind of assumed that the last one would be less important, and then at least for our purposes, distillation might be the most important. So I wanted to make sure to have some time for this. And there's another concept called merging, but as of the writing of the genai handbook, there's not much on that right now. So we're going to finish this model on fine tuning. And the metaphor is if you have a very large language model, we're going to call that the teacher. And you want to make a smaller language model for maybe your workplace, or maybe something you could literally run on your phone. The smaller language model will be called the student. Or sources. A couple of terminology from the mathematics that I myself found interesting. Whenever I go to seminars about artificial intelligence, I hear the researchers talk about temperature. So it's good that now I have a better idea what that is. You could see the capital T in this formula. This formula is the softmax formula, where remember, in addition to finding a maximum, you're also expressing the probabilities of the other possible routes or outcomes so that the entire vector adds up to 100%. What temperature is this update to the softmax formula where you could have a denominator there in the exponentials. This gives the AI developers yet another hyperparameter in addition to things like learning rate, hidden layer size, optimizer momentum. Here, the temperature is a positive number. If you ever hear a professor or someone say a zero temperature baseline, that just simply goes back to one hot encoding, ones and zeros for your classification data. Now, if you take that all the way to the extreme in the other direction, take capital T towards infinity, this becomes the uniform distribution. And if you're talking about a classification task where everything is uniform, that means that your model is simply performing random guessing. What temperature allows a developer to do is to make a compromise in between the two, where you might not want to always choose one particular route. And that was back in the day called a majority classifier in some settings. But of course, you don't want the system to be randomly guessing as well. So the temperature itself would have a Goldilocks principle that in some value for capital T, it would be just right for your situation. But at least for me, I was happy to know what the heck they meant by zero temperature. It was just something we knew before. I briefly mentioned the Kullback-Leibler divergence. The Kullback-Leibler loss function is used to measure the difference between two probability distributions. And what I see it as is an update to old formulas for entropy coming from information theory and how we made decision trees back in machine learning. These are, of course, also using logarithms. So this is also hoping for some speed up in training models similar to cross entropy. When we were talking about encoders and decoders, a popular development among encoders was called BERT, bidirectional encoder representations from transformers. Whereas in the public sphere, the decoders became very popular because that's what led to GPT, the generative pre-trained transformers. And I'm really hoping the next diagram shows up. Oh, thank goodness. When we're talking about encoders and decoders, the left-hand side, we usually refer to the BERT models produced by Google. And this is transfer learning, where AI will continue to learn from its existing data. Whereas the right-hand side, the decoder part of the transformer, became GPT, popularized by OpenAI, that will decode from its pre-trained embeddings to present output back in, say, English that will match what the user asked for. So once again, on the left-hand side, for the encoders, we're asking the AI to continue training itself. And then on the right-hand side, with the decoders, we're asking the model to give us something that is spoken in plain language that's interpretable. So for our purposes, the various applications for the encoders, such as BERT, very good for text classification. For data labeling, such as if you want to cluster your language models. It's good in recommender systems, dating back to the Netflix prize and recommending movies, for example. And I'd like to see the comeback of sentiment analysis, rating things, say, for example, positive, negative, angry, nice, that sort of thing. Where a lot of people are, of course, using artificial intelligence is with GPT, the decoded messages. That's good for content generation, such as if you want to help writing an email or an essay. And of course, we have also seen this being turned into conversational chatbots, such as maybe making a therapy system, maybe running ideas versus an AI to get an additional voice in the room. And of course, the customer service chatbots as well. So then let me quickly finish off with distillation. Once again, picture did not show up. Basically, distillation is that we want to achieve high accuracy, but with smaller language models. So that way we don't have to spend a lot of compute time. So for example, really quickly, if we ask a teacher to explain addition with two-digit numbers, where we have to carry a number from the 1's digit to the 10th digit, the teacher would talk about the whole system. What the student will retain hilariously in this model would still be able to do the same process, but would no longer to be able to explain the steps in between because they just cared about how to get from the problem to the solution, which I assure you happens in real life too. Not reading the
in that merging part, do the weightings have to be the same in the two LLMs or in the two teacher-student templates? I'm kind of curious, what if there is a significant difference in the parameterizations across the two models? how that affects the final output.
So yes, the data set itself, the prompts and the outputs should be the same between the teacher and student. We're hoping that the student model is much smaller in parameter space, the number of parameters. So almost by definition, it would have to have different weights.
Okay.
I briefly talked about chain of thought last week in instruct fine tuning, how the AI learns to deal with sentence structure and answer questions in context. So while the teacher might have the large paragraph on the top and focus on the green sentence and produce an answer in the format of blue, the student would be working maybe towards the bottom, just focused on the green context, which might be a slightly different context, and get an answer in the form of blue. So what Dilbert was an experiment in the distillation, going from in the top row 110 million parameters down to 66 million parameters. It was a savings time of about 40% in getting answers out of it. And on the Internet Movie Database, its accuracy only decreased from 93.5% to 93.1%. So very promising results at the time.